Alright, so for this next part, we're going to do another stability analysis, this time on the Crank Nicolson solution. So up here I have written for us the Crank Nicolson solution, and we're going to prove with this stability analysis that we don't need, there are no bounds on where it's stable. It's going to be stable everywhere. So last time we had R needed to have bounds of 1/2, but this time we're going to show that there are no bounds on U. So we're going to do very similar to what we did last time, where we have this equation for t, and we're going to plug it into these different t values we have. I already did some of that in the previous videos, so I just rewrote what I derived earlier at t at j at n, t at j plus 1 at n, and t at j minus 1 at n. And I have these two in their form where they're in relation to t at j at n. So we'll use those that I derived earlier. And then we're also going to need to use Euler's formula again, specifically this form of it. It's going to be very similar to last time. So, alright, let's get started. So, first, we're going to look at this side. On this side, we have t at j at n, which is this value here. And we're going to put everything in terms of it, just how we put these two in terms of it. So I'm going to basically factor this out of all of the terms, just right from the beginning. So we're going to do t, I'll give us a little bit more room. So we'll do t at j at n times, okay, so then for this first term, we have u, so it's going to be u, and then it's t at j plus 1 at n. So it's j plus 1 at n, which is just this. We factored out that, so then we're just going to have that left over. So it's going to be u times e at I, k, delta x. Okay, so then next term, factor that out, so that's just going to be plus 1 minus 2u. Alright, and then the third term, we're going to have the u again. This time, it's t at j minus 1 n. So that's this value. Factored that out, and we're just going to have this e term left. So u times e to the negative I, k, delta x. So like that. So that's this side. Now we're going to work on this side. So this one, we're going to factor out t at j at n plus 1. So t at j at n plus 1. Alright, so then the first one, we've got a negative u. And then this is at t at j plus 1 n plus 1. So it's very similar to this. This one. It's just that both of these terms will be plus 1. Because once again, it's the j term that's different between them. The n term is the same. So the n term, which is this part, is going to cancel out regardless. So I'm going to have the same thing over here. So that's negative u times e to the I, k, delta x. And then plus this part, we factored that out, so plus 1 minus 2u, and then minus u, which is that. Again, this is going to be very similar to this, where both of these are going to be plus 1. And n's factor out again, so we can just use this. So e to the negative I, k, delta x. Okay, so now we have this, and we want to factor it, or simplify it a little bit. So first thing we can do is use Euler's formula. So we'll still have this t at j at n, but then you'll notice that this term and this term are similar to the Euler's formula, where we've got the positive exponent and the negative exponent. So we can make that as 2u, because the u is still there, times cosine of k delta x. Because in this case, this general x here is represented by this k delta x that we have. So then we'll have that plus the 1 minus 2u. Okay, and then we can do the same thing with the other side, where you have t at j at n plus 1 So once again, these two terms can be used with Euler's formula because we have the positive exponent and the negative exponent. So we have negative 2u cosine of k delta x, and then plus 1 minus 2u. Alright, so I think one of these should be plus. I believe it was this one that's plus. I'm going to write this wrong. Yeah, I think it's that one that's plus. Alright, so yeah, that was just a mistake when I was copying that line down. But I think we're good now. So next, we're going to want to solve for this side, so we're going to divide this side over here. I guess we can, before we get to that, let's factor out these two u's on each side. So I have t at j at n times 2u times, okay, we'll put this 1 plus up front. So we'll have 1 plus 2u of cosine k delta x, and then minus 1. Alright, and then it's t at j at n plus 1. And this time we again have this 1 up front, so 1 plus 2u times 1 minus cosine of k delta x. Alright, so then at this point now we're going to solve for this and divide both sides. So I'm going to put this over here, so we got t at j at n plus 1. So that's that, and then we're going to have this side, so we got t at j at n, and then we've got this as a numerator, so 1 plus 2u cosine of k delta x minus 1, and then that is over this, which is 1 plus 2u times 1 minus cosine of k delta x. Alright, so then at this point we can see these are very similar. It would be nice if we could cancel these, and we can if we factor out a negative essentially from one of these. So we're going to factor the negative out of the top side. So we're going to have t at j n plus 1 is equal to t at j at n. So then factor out the negative, so it'll be negative 1 minus 2u of 1 minus cosine k delta x over 1 plus 2u of 1 minus cosine k delta x. Okay. So there you can see that these two pieces now cancel. Make sure this is supposed to be positive. Hold it. Alright, sorry, I see where it is. So when I factor the negative out on this side, this doesn't have parentheses around it, but I kind of acted as if it did. So when I factor this out, this negative I factor out of this is only going to be multiplied by this negative, or by this 2u, not by the 1. So that's where that negative came from, but it's not supposed to be there. All right, so then at this point, we have, we're basically done, and we can look at this. So this term I mean, it doesn't cancel out. That's not what I was thinking earlier, but like, you can see that this term here and this term here are like the same. So we could simplify that and say that like, say W is equal to 2U times 1 minus cosine of k delta x. And we could simplify this as t at j at n plus 1 equals t at j at n of 1 minus w over 1 plus w. And that might make it a little bit easier for us to see what's going on. But first let's look at this w term. So within this w term, this part's always going to be positive because u is always going to be positive. Within this, cosine will always be less than 1. So at its lowest, it'll be -1. So 1 minus -1 is going to be 2. At its highest, it's going to be 1. So 1 minus 1 is 0. So it's always going to be greater than or equal to 0. So it's never going to be negative, always a positive number. So then if we take what we know there, because it'll be multiplied by a positive, so this whole thing will always be, w will always be greater than or equal to 0. So if we take that and apply it here, so we know that's always going to be positive, and that's always going to be positive. And hold up. Alright, so we know that those are always going to be positive, and so since 1 minus a positive number over 1 plus that same positive number, this denominator is always going to be larger than the numerator, meaning that this value in general is always going to be less than 1. And if you remember from the last video, this value here being less than 1 is what we were looking for, and that's why we needed to put a bound on r last time to say, hey, it's only less than 1, if r is, like less than 1/2. But in this case, it doesn't matter what u is, this will always be less than 1 regardless, and that is why Crank Nicolson is stable everywhere, and it doesn't need concept of stability or anything. So there we have the stability analysis for the Crank Nicolson.